Hello, everyone. Come in. Anybody have any questions while we're waiting for everybody else to come in? Looks like we barely got in here in time.
When did you say your office hours were?
So Monday, Tuesday, Wednesday, well, Monday and Wednesday, I'm there at 8 a.m. You should try to let me know you're coming though, but I'm there from 8 a.m. to 9 a.m. And then on Monday and Wednesday, I also have usually by around because I do the lab first, usually by around 10 o'clock. So any time between 10 and noon on Monday and Wednesdays, also an office hour. So we got 8 to 9 and 10 to noon. And then, of course, after this class is a meeting time. And then on Tuesdays and Thursdays, I have 8:30 to 9, or excuse me, 8 to 8:30. And then I have again from about, I think it's from about 9:30, no, about 10:30 till 12 on Tuesdays and Thursdays.
Okay. Are you going to be at your office hours today?
The office I have basically I spare time at the end of this, so you have that. But I've already been to school, so you can certainly stay late and ask me questions afterward if that's what you mean.
Yeah, I mean, I kind of have quite a few questions, so
Yeah, that's no problem. Otherwise,
I
like I
don't
said,
want
I'll be in tomorrow at 8. My class starts at 8:30. But that's a lecture from 8:30 to 9:50.
I mean, Zoom's fine with me. Zoom is definitely probably preferred
Oh, Zoom works
on
for you
my
instead of coming to campus? Yeah, just stay
absolutely.
after. This class and my Tuesday, Thursday class happens the same time. They're both open as office hours. So and I put a link to those in your Canvas course. So you
Okay,
can
so
always come
after this
in.
class, should I just hang out here or go over to that other
No, just
Zoom?
hang out here because literally it's just the same meeting. So people have a
Okay,
copy
cool.
of this access code from all my classes, so they can all come here at at the end of class. Which I tell them to show up about 6:35 because class is over at 6:40, and in case I finish early, I'll know they're here to
Okay,
ask questions.
cool. All right, thank you.
No problem. Was that Eddie I was talking to? Yes.
Yes, sir.
All right. Anybody else have any questions? I did just send out an email. Still waiting for if you have any questions, you can type them or just speak up. But I did send out an email today. I got the difficulties worked out with the tests. I got them posted, but I then looked at my calendar, which I had set up improperly, and it turns out your test is not next week. So what class day do you have or what day of the week do you have your lab in this class?
For me, Monday.
Monday. I
Mine's
think
on Monday also.
Yeah, I think they're all Monday. Okay, so the way Monday works, we're now behind a week. So you guys will actually have, I think it's the 25th is the Monday that will be, it's either 25th or let me see, fifth, I think it's 15 through 20 something. So it's essentially the third lab from today is when your face-to-face test is. So I might fit in. I already have one online test. I'm definitely going to fit in another one, but I might actually fit two in. So just to be prepared for that. And either way, you'd have a whole week, but it all depends on how many chapters I cover. So right now you've got chapters 1 and 2 outline online tests that's due. I pushed it back to the 12th because I thought literally the class meeting or the face-to-face test was the 12th, but that's not true. Like I said, it's quite a bit later. And once we finish chapter 3 and 4, I'll probably consider putting that other one up. So
I had a
go ahead, John.
I had a question. I had a question about if you saw my email about my weekend.
I did not see that, but I haven't got up to catching up my weekend emails either.
So I sent an email over late Monday night. I was supposed to do my work this weekend, but the internet at the house I was staying at this weekend went out. So my full day of work turned into 0 hours. So I'm a little behind on my homework and classwork. So I was asking about exemption for late stuff. this
Yeah,
week.
that's no problem. I usually don't give any extensions like that, but I will. It's not a problem
Okay.
because I haven't been
And
keeping up with the stuff as rapidly as I'd want to. So I will just let me know when you do finish that homework that was due, and I'll address it. And anybody else has a similar problem, let me know. I'll help you. When I do stuff like that, I usually give the ones that finish it on time, I give them a couple points extra credit. So that might be the difference.
okay. All right. Thanks.
You are allowed to use a graphing calculator. I don't mind you using that. And I know that it has equations in it and all that good stuff, but that's all fine. Anything else? All right. So when we last talked, we were in chapter 19. We're almost finished with chapter 19, but I was in the middle of a problem, and it was actually a problem from the book, so it wasn't that big of a deal. But the problem in the book was basically how much energy does a freezer have to remove from 1.5 kilograms of water at 20 degrees Celsius to make it ice at -12? So I actually worked that out. It's exactly the same as example 19.6. So you can look that up. I don't remember if I finished the calculation before I let you go or if I did it after I let you go. But either way, we're not gonna finish that up. You can look right at the example in the book. I've sort of explained it all. And the problem I'm getting ready to do is a more advanced version and more helpful. So it's really way more important that we do that one. So thanks, Richard. Let me know the same thing. So what we're going to do is we're going to solve a problem. I've actually, well, crap. I took the time to write it down, but now it's disappeared. Let's see if I put it somewhere else. Yeah, that's what I did. Okay, hold on, folks. I'm going to try to lasso this problem because literally my Good Notes has a little lasso icon. Okay. Now I'm going to paste it right here. I know you aren't looking at my screen, but don't worry. Okay, it decided to take my little link at the top too, so I'll just leave it there. And now I'm going to do share screen. And we're going to hope that it works because that would be handy. Put that over there. I still want my chat to come up in case anybody needs me. I'm waiting for that. That's going to be good right down here. Okay, so I've got that set up and now it should be coming to my computer. Well, it's acting like it's not coming to my computer. So it did something wrong. Let's try again. Share screen, iPad via AirPlay. There you go. Now it's coming up. All right. So it should come up any second now. So I'll read it to you, and then of course you can read it again when it comes up here. But it says a 0.750 kilogram block of ice. Has a temperature of -15.0 degrees Celsius when it's put into in a cooler that contains 3.50 kilograms of water at 21.0 degrees Celsius. What will the final temperature be? And I'm going to talk a little bit about the phases or the phase of this state of water when it's done, or ice and water or whatever. Okay. So does everybody understand that question? So I'm going to use a couple of things here. One thing I'm going to use is Q lost. In other words, all the things that are losing heat is equal to Q gained. So all the things that are taking in heat, I will add all the things that are losing heat, add their heats together and put them on one side of the equals. And then I'll take all the things that are gaining heat, add those heats together and put it on the other side. And Brandon has his hands up. Go ahead. You can
Was there
type
a
it.
lecture on Monday?
What's that? No, there wasn't. No, I'm
Weren't
actually
we talking about
remembering from
kinematics
last week.
before that?
Sorry. Yeah,
I
we
feel
did
like we
have
were
class
talking
Monday.
We did have class Monday?
We did not.
Oh, okay. I thought we were talking about kinematics last time we were in class. Like, I
Holy
thought
crap.
we were doing...
Yeah.
We definitely were.
I just remembered what happened. I'm sorry. This is terrible.
Is it 14.6 degrees?
It actually came up to like 5 degrees Celsius, believe it or not. What you're forgetting there, I got about that 14 too, but you forgot to take into account that all the ice will melt. So there's another, that ML equation that I was in the process of writing was relevant. But yeah, sorry about that, guys. Well, I'm going to try to figure out some way to blame y'all. That's what I'm going to do. That's just, I feel better about myself if it was your fault. So
Hey, I'll take the heat.
yes, kinematics is where we're at. And actually, the very last thing we did was we started working a problem. Actually, let's see if I even have it listed now. We started working a problem. Here it is. This is 8:30. Oh, yeah. Okay. So we just got up to integrating, for instance, A as a function of time and determining what the position as a function of time and the velocity as a function of time was. That was essentially all of chapter 2, except we didn't cover very much about free fall. So that's what I'm going to do now. I am going to open up that same document I just had, and I'm going to start off with solving a problem of basically tossing a ball in the air. So this premise is we're studying kinematics, so we don't yet know exactly what the deal is regarding how accelerations are made or how velocities are made. We just know that if I have an initial velocity, an acceleration, and that kind of stuff, I can derive an equation for the velocity as a function of time and the position as a function of time. And just as long as I have enough initial conditions, I can do that. But now we're going to study free fall, and what Galileo discovered, which you've probably heard the story about the Leaning Tower of Pisa, and he realized that you could drop a ball and a feather, and if it wasn't for the air resistance, the bowling ball and the feather, which obviously Galileo played a lot of bowling when he was back then in that time. So yeah, when Galileo dropped a bowling ball next to a feather, the feather and the bowling ball fell at the same rates. What he realized was that acceleration was a uniform constant thing, and specifically he's the first one that really, or at least the first one that I know of, that actually defined what speed was, what velocity was, what acceleration was, and in fact he went further and said constant velocity is when an object covers the exact same distance for a certain interval of time and every other interval of time that's the same length. So if you saw that at one point in a ball's motion it rolled 3 meters in 1 second, then every other 1 second interval would require it to travel a distance of 3 meters. Okay, that's what constant speed / velocity is. Constant acceleration has a common change of velocity for a given unit of time. So again, if you considered a unit of time to be, say, 1 second, and the velocity at one point at the beginning of a 1 second interval and the end of a 1 second interval were, let's say, 8 and 11 meters per second, then clearly any other 1 second interval will cause a 3 meter per second increase in speed. And that's what constant acceleration means. And by figuring all that out, he then reached the conclusion that when you drop a ball, it actually accelerates at a fixed rate, and that rate is 9.8 meters per second every second. And I like saying it that way, meters per second every second, because even though it's exactly the same as this number, g is equal to 9.80 meters per second squared. Mathematically, that's completely correct. There's nothing wrong with that. There's not even anything wrong with the words of saying meters per second, but I prefer my students to say 9.80 meters per second every second. So they'll have always in their mind that idea of what acceleration is. It's a change in velocity for a given unit of time. And if it's a constant velocity, that change in velocity will always be the same for that unit of time, whether it's 1 second at the beginning, 1 second in the middle, or 1 second at the end. Okay, so the acceleration due to gravity has a magnitude of 9.8 meters per second, and a lot of people just says automatically g is negative 9.8. That's not really the case. There are problems where it's more convenient, for instance, to create a coordinate system with the x-axis or even the y-axis pointing down as positive. If that's the case, then g would be a positive value. positive 9.80 meters per second. And if you threw a ball up in that same reference frame, its initial velocity would be negative. But if you threw a ball down, then it would be positive. And that's exactly a case of why it is convenient, or why it is sometimes convenient to choose downward as the positive direction. For instance, if I threw a ball down at a certain speed, and then allowed it, to take off or whatever, both the acceleration and the initial velocity would be positive. So I wouldn't have any negatives to deal with. All right. All right. So what I'm going to do now is I'm going to show you how to use this idea that gravity is 9.8 meters per second every second. Again, this is like 0 to 60 in 4 seconds. And if that was really a constant acceleration, which I've told you, cars generally do not have constant accelerations from 0 to 60. But if it was, then what that would mean, in 1 second, it would go from 0 to 15. And in 2 seconds, it would go, in the second, it'd go another 15 meters per second, which would be from 15 to 30, and then 30 to 45, and then 45 to 60. So this means the same thing. It's going to go in 1 second, 9.8 meters per second change. And then the next one, another 9.8, which would be a total of 19.6, and so on and so forth. So let's imagine a ball. I can't believe I started giving you 242 problems. A ball is thrown upward with a speed. I really should have put that A a little further apart. With a speed of, dang it, I got to put this farther apart too, of 19.6 meters per second. A, how high will the ball go? B, what will be its velocity at t equals 1.00 seconds, 2.00 seconds, 3.00 seconds, and 4.00 seconds. And then that was part B. Part C will be after 7.00 seconds, how far below the ball's initial height. In other words, when I release it from my hand, say initial height. So after 7.06007 seconds, how far below the ball's initial height will the ball be? And then finally, part D, how fast will it be going? So those are basically, I made a multi-part problem so you can sort of see how we use all the various equations. This is not one where we're required to use the quadratic formula, for instance, to solve for our time, but it still is it covers just about every other thing. So it's a good one robust problem. And in fact, I'm going to implement some stuff so you'd see exactly what it is. So let's start off with our solution. So in order to make the solution, I've got to figure out exactly what it's telling me. So what it's told me is the ball was thrown upward with a speed of 19.6. So I'm going to say V0 is equal to positive 19.6 meters per second. And by doing that, what I've assumed, and you can call it a y-axis or an x-axis, doesn't matter, but what I've assumed is that my axis, the positive end, is pointing up, and therefore the bottom end is pointing down, and that's the negative side. And I'm going to go with the origin being exactly at the height at which my hand was when it released the ball. Okay, so that's what I'm doing with the variables I'm choosing and the signs that I'm giving them. So there's the initial velocity. We also know that the acceleration, since the initial velocity is up and positive, that means the acceleration, which we know is down, is negative 9.80 meters per second every second. So we know that. And then part A, they want to find Y max. That's what I'm going to call it. And all it really means is the maximum height it reaches. Okay. Part B, I would like to know its velocity at various times. So I'm going to say V of 1.00 seconds, V of 2.00 seconds, V of 3.00 seconds, and V of 4.00 seconds is question mark. So that's really what part B is about. I'm mainly doing that so you can see what I'm talking about when I say the acceleration is 9.8 meters per second every second. I want you to actually physically see what that is by me working this problem for all those different times. At C, part C says after 7 seconds, how high will it be? So I'm going to say Y of 7.00 seconds is equal to question mark. That's what part C wants. And then part D is how fast will it be going? So part D, I'm going to say V of 7.00 seconds is equal to question mark. That doesn't mean that I'm necessarily going to derive an expression for V as a function of time. I'm just going to use my kinematic equations. But the main thing is I need, at that point where we just found out how low it will be, I want to also know what its velocity will be at that time. So if I start off with part A, I can say, well, I can ask you a question. When I throw a ball upward, it goes up, 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 and then all of a sudden it starts going back down, 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 down. What is the velocity that it has at its highest point?
Zero.
Zero, exactly. Okay. So that's a key thing to understand. And that's just what's somewhat of a common sense conceptual physics idea. Okay. It's just something you're used to. But if you don't necessarily see why is that actually true, think about it this way. If an object had some very, very small positive velocity, no matter how small it is, the object will continue to go up a little bit because that's the direction it's moving in. And even though gravity is pulling down on it, trying to slow it down, it can't do it all in an instant. So it's going to take some small amount of time for it to go from that small net velocity upward to zero. Okay, so it's always going to be still able to climb if the velocity is not zero and in fact is upward or positive in our coordinate system. Additionally, if the ball was actually moving downward, then its new velocity is in the negative direction, and in fact it must have been zero sometime in the past, so that can't be the max height either. So what that tells you is, yes, the final velocity has to be zero when it reaches its peak. So I'm going to say V equals zero implies what we're going to do is say zero equals what I'm using now. Actually, it might help to write that first. I'll go ahead and write that first. Let me do that. What I'm using is this equation. V is equal to V0 plus AT. That's one of the kinematic equations. It can also be looked at as the average acceleration or just the acceleration for a constant acceleration problem. So what I'm going to do now is I'm going to implement that V equals zero And by doing this, this will allow me to use y equals 1/2 at squared plus v0t plus y0. So I could solve that first equation for time and then plug it in the second equation. That's a perfectly cromulent way to do it. Okay. That being said, it's not necessarily the smartest way for a test, because if you're taking a test, what happens if you made an error on that first equation and then you did the second part completely right, but you just made a careless error in the first part? So you're going to get a wrong answer. And unless someone's actually looking exactly what you did, you're going to get no credit for it. So if there's a way to do it without first solving for a number that you didn't necessarily need to know, and then using that number to find the answer, don't do it unless you have to. Okay. Or do it as a second step just to verify your answer. That's another fine reason. So that is one way we could do it. So that's one way. But there's another way we can do it too, and it makes use of a different equation. And that different equation is, of course, v equal, oops, I did not mean to say in red and blue, v equals 0, and I would take and plug that into v squared is equal to v0 squared plus 2 times a. And since I'm calling up the y direction, I'll call that y minus y0 instead of x minus x0. So everybody understand that I can use that equation to find the height? That makes some sense, right? So we're going to plug in that 0. I'm also going to stipulate what I said physically, what I actually said a few seconds ago. I keep using this word physically. I don't know why it keeps coming to my mouth. But anyways, what I said a second ago was when the ball left my hand, that's the height that I'm going to consider the location that I'm going to consider the origin to be. So I'm going to remind you that y0 is equal to 0, and I'll put it right here. Okay. So with that being said, I can now say 0 squared is equal to 19.6 meters per second squared plus 2 times negative 9.80 meters per second every second times y minus y0. And that part right there is 0. But the y is what we're wanting to solve for. Okay. So now I can do 19.6 squared, and I'll leave that on its side by itself. And that is 384.16.
Can you read that last part of the equation after 0 squared?
Yes.
19.
Yes, it's 0 squared equals 19.6 meters per second squared plus 2 times negative 9.8 meters per second, close parentheses, times parenthesis y minus y0 close parenthesis.
Thank you.
No problem. It's good that I asked that because I did write it quite small. Or it's good that you asked that, I mean, because I did write it quite small. So since you took a meter per second and squared it, the units for that's now meters squared per second squared. So that's what the 19.6 squared is. The other term, notice that negative in the 9.8 is going to make that a negative term. So I'm going to pull that to the other side of the equal sign and make it positive. So 2 times 9.8 is in fact 19.6 meters per second times y. Okay, so that's what I get there, because 2 times 9.8 is 19.6. So I can now solve for y, and the way I solve for y is dividing both sides by 19.6. And of course, when you divide 19.6 squared by 19.6, you get 19.6 again. So what I'm going to say is 19. Ooh, excuse me. 19.6. Yeah, I think that's right. Right. So when I divide the 384.16 by meters squared per second squared by 19.6, the numerical part of the answer is 19.6. But what you'll see is one of the meters in the top numerator will be canceled out by the meter in the numerator of the bottom. And both of the second squares will be canceled out. So it'll just come up to meters. And in this case, I got y equals 19.6 meters. So that's actually what we call Y max. Let me do that too, since I did in fact call it Y max. I'll say that, and this is Y, not to be confused with X. So there's your answer to part A. Anybody have any questions on that? All right. Now, just to show you that that other way would work, notice if I solve 19.6, so I'm going to say alternate. 19.6 meters per second is equal to, ooh, not that way. Sorry, I was using V0 V equals V0T. Excuse me, V equals V0 plus AT to write that down, but I ended up writing the wrong number first. And I don't know why other stuff is here. So this is just going to be an alternate solution. And since it took so many button clicks, I should have just erased it. But anyways, here's the alternative. So the alternative in this case would have been 0 is equal to 19.6 meters per second plus negative 9.80 meters per second times t, which gives me t is equal to 2.00 seconds. Okay, and now I can take y equals 1/2 at squared plus v0t. I can do 1/2 times negative 9.80 meters per second times 2.00 seconds squared plus 19.6 meters per second, that's the initial velocity, times 2.00 seconds plus the initial position or the initial height, which is 0 meters. So you can see all this is going to make meters. Not only that, what you're going to get is the y max is actually equal to, notice basically the first term is 1/2 times negative 9.8 times 4. So 1/2 times 4 just gives you 2. So in fact, this whole first term is just 2 times 9.8, but negative. However, the other one is just 2 times 19.6, which is really like 4 times 9.8. So you could also figure it out that way. But you can also, of course, put it in the calculator. But I just wanted you to have some understanding that since 19.6 happens to be exactly twice 9.8, that makes it a little bit easier because I've got a term of, well, 4 divided by 2 is 2, like I said, so of negative 19.6. That's the first term, and then a term of twice 19.6. So 2 times 19.6 minus twice 19.6 gives you 19.6. So the answer, it turns out to be 19.6 meters, which is exactly the same way, or the same answer we got when we did it the other way. So everybody follow that? I'm sorry, I do tend to explain the arithmetic I'm doing just so I don't have to put it in a calculator. I'm really doing it real bad now because I left the light off in the room and the blinds shut. So now I can hardly see even my calculator. But I apologize. I know sometimes most people cannot understand when someone's explaining how they're working out their arithmetic in their head. So you feel free to ignore me when I go on one of those tangents. But you have it written there. You can just throw it in your calculator and double check. But yeah, it comes up to the same answer both times. So that's a good thing. And remember, the more ways you have to solve a problem, the more likely you are to actually do well on the test, or any test for that matter. And also, the more times or the more ways you do it, if you keep getting the same answer, you're more confident about the answer being right. All right, so let's look at part B now. I'm going back to my red marker. I'm going back to my red. So in this case, what they're wanting to know is, what is the velocity after all these times? So we're going to use V is equal to V0 plus AT. So what that means is V of 1.00 seconds is equal to 19.6 meters per second. That's the initial velocity, minus 9.80 meters per second. Okay, that's the A term, or the A factor in the second term. And then, of course, I'm going to multiply that by 1.00 seconds. So what I basically have here is 19.6, which is twice 9.8. And twice 9.8 minus 9.8 is just 9.8. So that's the velocity at 1 second, 9.80 meters per second. Now we're going to do the same thing for the other parts, but of course this will be 2.00, 3.00, and ultimately 4.00. That's the only thing that's going to change for the other parts of this number, part B. So we had 19.6 minus 1 times 9.8. And now the next term will have 19.6 minus 2 times 9.8. Notice 2 times 9.8 is 19.6, so we're going to get 0. So now I can say V of, actually, let's go back to red. V of 2.00 seconds is equal to 0 meters per second. And we sort of knew that already because we solved it in part in the alternative version of part A. We found that the time would be 2 seconds. I'm going to point out something else about that in a second, though. So V of 3.00 seconds. Now that's going to be 19.6 minus 3 times 9.8. So that actually gives me a negative 9.8 meters per second. And then finally, V of 4.00 seconds is equal to negative 19.6 meters per second. And I think you can see that that's going to be, of course, from 19.6 minus 4 times 9.8. So it's literally 2 times 9.8 minus 4 times 9.8. Of course, 2 minus 4 is 2. So this would be a negative 2 times 9.8, which is why I got 19.6. Any questions on that part? Again, speaking out my arithmetic.
Can you zoom in?
Yes, go ahead.
Can you zoom in at the bottom?
Yes.
Can't see it.
Gotcha. Actually, let's turn it this way and see if I can do it better. I think you can get away without seeing that part. Did you get all that?
Yeah, I got it.
Thank you, Sherrod. Yes, this is called free fall, and throwing it up, throwing it down, that's all free fall, by the way. What makes it free fall is that we're going on the assumption that the acceleration due to gravity is really the only acceleration it has. In other words, is not going to be affected by air resistance. That's sort of the best way of thinking about it. So anything that doesn't have a drag force on it is going to be considered free fall, as long as it's around the planet where there's a gravitational field or something. Okay, so we've got part B. Part C, we want to know what the elevation is at 7 seconds. And part D, we want to know what the velocity is at 7 seconds. But before I go on, I want to stress that other point to you about this B. Okay. This is where I want you to understand exactly what I mean by saying the acceleration due to gravity is a constant, and the constant is 9.8 meters per second. And notice it points towards the ground, which is what we call the negative direction. So what you're seeing by these velocities at 0 seconds, which was positive 19.6, and then the velocity at 1 second, 2 second, 3 seconds, is literally going and looking at a 1 second interval each time. And for instance, according to the acceleration being negative 9.80 meters per second every second, you expect the 19.6 meter per second initial velocity to drop by 9.80 meters per second after 1 second. And lo and behold, if you take 19.6 and subtract 9.80 from it, you get again 9.80 meters per second in the positive direction. So that's what that first answer was. Now, of course, it's constant acceleration. So every 1 second interval is going to have the velocity change and make itself more negative by 9.80 meters per second every second. So if it was 9.8 after 1 second, it's going to go down another 9.8 after a second. So that would be 9.8 minus 9.8. And that's why we got a 0 for that 2 second mark. And it goes further. Now it's 0. If I wait another second, the velocity is going to go down another 9.80 meters per second, which is exactly what V of 3 is. V of 3 is negative 9.8. So every time the velocity is decreasing by negative 9.8 each second. And that's what I wanted you to see. And that's also why it's nice to think of acceleration as 9.8 meters per second, say, lost every second. Okay. Everybody get that? Might have to mull and stew over it a little while. It is sort of it's one of the bigger concepts of kinematics. Even though kinematics is one of the easier parts of physics in general, it's still one of the bigger concepts. So now we're going to go, now that I've explained that part, we're going to go ahead and look at part C. So we want to know what y is after 7 seconds. So I'm going to do that now. Y of 7.00 seconds is equal to 1/2 of negative 9.80 meters per second every second times 7.00 seconds squared plus the initial velocity, which is 19.6 meters per second times 7.00 seconds plus the initial height. We said y0 was 0, so this would be plus 0 meters. And I'm just putting that meter on there to remind you that all this stuff is having the right units. So if I take 9.8, multiply it by 1/2, and then times 7 squared, which is 49, I get 240.1. So this is going to be 240 negative 240.1. That's actually one extra sig fig than we can really have. So I'll underline that 1. Now the other term is going to be 19.6 times 7, which is 137.2. So this is plus 137.2 meters. That 2 is only supposed to have 3 sig figs, so I have to underline the 2. So now what I'm going to do is I'm going to take 137.2 and subtract from it 240.1. Because that's what we have to do here, because the bigger number is actually negative. So this is negative 102.9 meters is the actual answer. So that is what y of 7.00 seconds is. So that's part C. Any questions on that one? All right, there's a part D, and that part D is really where we're just supposed to find out what the velocity is at that point. And again, there's a couple ways you can do it. You can use V equals V0 plus AT, which is really nice, and it is a vector equation. But you could also use v squared is equal to v0 squared plus 2ay minus y0, employing the y that we just found for 7 seconds. Okay, so we could use either one of those. Obviously, that second one is using a calculated quantity, so that's not that helpful. But if you look at the other one, it's pretty much going to use a calculated quantity as well. It's going to use the fact that the time was 7 seconds. Well, actually, no, it's just 7 seconds. So I don't have to even take into account that it was 2 seconds to reach the top. So we'll do that first way, and then I'll show you how you can do the second way, just to show you that it gets the right answer. So V is going to be equal to 19.6 meters per second plus negative 9.80 meters per second times 7.00 seconds. And of course, we already figured out that 9.8 times 7 was 137.2. So this will be 19.6 meters per second minus wrote the 3 before the 1, minus 137.2 meters. I'm just using the fact that that happened to be part of the answer or part of the equation y equals 1/2 at squared v0 plus v0t plus y0 in the previous one. So that's why I was able to just quickly throw out that number. So now I'm going to take 19.6 and subtract from it 137.2. And that's going to give me negative 117.6. Okay, hopefully that works. Let's see. And let me check my math too, just in case I made a boo-boo in calculating 9.8 times 7. 9.8 times 7. Oh, yes, I definitely made a mistake in calculating 9.8 times 7. Ah, that's what it was. Anybody see how dumb your teacher is? Notice this term right here. That was what I thought is this, and it is that, but the problem is that's not the same as that. So that's just me being a goober. So let me put a mark through this and say no. And instead, the actual answer, when you multiply 9.8 times 7, you get 68.6. And notice that's yes, meters per second. So now what I got to do is take 19.6 and subtract from it that 68.6. And that gives me, in fact, that gives me negative 49.0 meters per second, which is V of 7.00 seconds. Now, the negative is just indicating that the ball is moving down at that point. It clearly went past the catch because the catch took 2 seconds. I mean, the throw went 2 seconds before it came to a stop. And then, of course, it only takes 2 seconds by the symmetry of the problem to get to the same height as where it was released from. So at the 4-second mark, it's just passing your hand. So you expect it to be going exactly the same speed, but in the opposite direction, i.e. negative 19.6 downward. But in this case, I said the velocity at 7 seconds. So it's continued to increase the magnitude of the velocity by negative 9.8 meters per second every second. So each of those seconds added up, and that's why we got such a large negative number. And obviously, it should be pointing down. Now, we could have done the other way, and that's what I'm going to do now, just to show you get the same answer. So the alternative, and feel free to stop me if I'm going too fast or you need help on anything. So what I'm going to say is the alternative is V squared is equal to 19.6 meters per second squared plus 2 times negative 9.80 meters per second every second times, now this y is what we know is 102.9, so it's going to be negative 102.9 meters minus 0. Okay, so that's the final height we know from the previous problem. Now you can see this is not a vector equation, so we're actually going to have to figure out some conceptual stuff on this one. So what I'm going to do is I'm going to first square 19.6, which we did that before. I think it was 240.1, but I'm going to do it again just to be sure. 19.6 squared is nope. It was not 240.1, it's 384.16. That's right, I remember that. So this would be v squared. That's a horrible looking v. V squared is equal to 384.16 meters squared per second squared. And then 2 times negative 9.8. So 2 times negative 9.8 times negative 102.9 gives me positive 2016.84. Now I've run roughshod over sig figs. Notice this unit does work out though. We at least got that part right. But I have run roughshod over the units. I had 3 sig figs and I squared it. I got that 384.16. So that means the 1 and the 6 are not significant. Again, with the multiplication in the other term, it was 2, which is to an infinite number of decimal places, 9.8, which is 3, and negative 102.9, which is 4. But really, to be honest with you, that 4 only has 3 of them are significant. But either way, you'd still get 3. So really, the 6, the 8, and the 4 in that term are not real. They're real. They're just not significant. Okay. So now we've got all our stuff figured out that way. I've got to add these two, and that's going to be plus 384.16. And basically, I just took the last answer, which was the 216.84, hit plus, and then 384.16, and that's giving me 2401 meters squared per second squared. Now it's crazy that it got such an odd number, 2,401. But check this out. Now to solve this equation, V is going to be the plus or minus square root of 2,401 meters per second. This actually had a doubtful digit in the 1 spot because when you add 384.16 in 2016, ooh, it's worse than that. And 2016.84, there's a doubtful digit in the 1's place on the on the 216.84. So that actually means that the 1's place is completely insignificant, and the 10's place is where we got to start it at. So anyways, we'll keep an eye on that. That means that figure right there is insignificant. And here's the part that I said happens because it's not a vector equation. We got to physically make the decision. There I go with the word physically again. We've got to make the decision ourselves as to whether the velocity should be negative or positive. I would argue, knowing that it was thrown up at 19.6 meters per second, which happens to be twice 9.8, then I suspect it's going to take 2 seconds to get up, 2 seconds to get back down. That's a total of 4 seconds. And all that after the 2 seconds is in the negative direction. So I'm going to go with the negative answer. And in fact, here's the cool part. The square root of 2401 is just plain old 49. And that actually is 3 sig figs, so I can call that 49.0 meters per second, which is exactly the same answer we got before. Anybody have any questions on that?
I got a question.
Yes.
Why would we ever do it the alternative way? That seems messy and
It was, but sometimes in the heat of a test, you might forget the equation V equals V0 plus AT. That gives you a backup. You can also give yourself another check just because maybe you got the answer and then you looked in the back of the book or you looked on the MyLab and Mastering and found that your answer didn't match. So you might want to try it a different way just to see if you get the same answer, because it could have been something with the algebra of one way you did it versus the algebra of another way. So it's always good to have a couple ways, but I in general agree that's a much more sucky way compared to the other one.
understood. That makes sense. Thank you.
All right, so we got all that, and you now have this neat little random tidbit fact that evidently 2,401 has a square root of 49. So if anybody just happens to say square root of 2,401, you can blurt it out like Rain Man. I think that'd be awesome. Anybody else have any questions? All right. So I'm gonna do what I did in my class today, specifically in my face-to-face class, just because I kind of like it better in the kinematics portion than I do doing it in the projectile motion point, a part of the text. So in this case, what we're actually going to do is I'm going to examine a case of a problem with air resistance. So let's imagine dropping a ball from a very tall height building or mountain or cliff or something like that. I'm going to just drop it so it has initial velocity V0 equal to 0. It's going to be going in the downward direction, and that's going to be the positive direction for me. And that's also the direction of the acceleration, g, being positive 9.80 meters per second every second. So that's what we're going to do. And in fact, if you imagine the ball in space, it turns out that the force of gravity, which is also called the weight, is actually just a force given by m times g if this thing has a mass m. Okay. And as I said, this is going to be what I consider my positive, let's say, y-axis. Okay. Now, it turns out also that if you include air resistance, then there's going to be a drag force, and that drag force would be back here. And there's a couple different ways you can model this, and it basically, it works really well one way in certain situations, and one way work really well another way in other types of situations. So one of the ways is, in fact, that the force sub drag, F sub D, the drag force, is actually multiple of B, some number, times V, the velocity. So in general, this number B will definitely depend on the cross-sectional area of the thing falling. So for instance, I could jump off the Empire State Building and I could wear one of those flying squirrel suits like you see these people doing skydiving and stuff that's got like wings draped under here and all that good stuff. I could wear that and spread my arms out really, really wide. And in fact, if you painted an outline of my body, that would normally be the cross-sectional area, but because I got a squirrel suit on, it's even got those webs between it. So that area, which is perpendicular to the velocity, is what that B depends on. That's one of the things it depends on. The other things it depends on, for instance, is the viscosity of the air or the density of the air, that sort of thing. So that B can take into account all of that stuff. So now those are the two forces. And since that BV is acting in the negative direction, Newton's second law, which says the total force is equal to mass times acceleration, would just give us that, let's say, mg minus bv is equal to m dv dt. Remember, acceleration is defined to be the velocity, the derivative of the velocity with respect to time. Technically, it's a vector quantity, so I can put arrows over both of those, but we're just talking one-dimensional motion. So the directionality of that is just basically the sign. So it shouldn't be too much of a problem. So now that we have that equation, F equals ma there, where it says mg minus bv is equal to m dv dt, what turns out a good thing to do is multiplying both sides by 1 over m. And in fact, this equation that I have is called a differential equation, and it's probably the very first differential equation you'll solve in your differential equations class. It's called a separable differential equation in the sense that you can take dv and dt and you can separate those parts and get everything that is a function of v either multiplied by or divided into dv, and everything that's a function of t can be set up to be multiplied by or divided into dt. So that's what's going on here. When I carry out that division, I end up getting g minus b over m times v is equal to dv dt. Now, what I'm going to do is multiply both sides by dt and divide by g minus b over m times v. So when I do that, I am going to have, oh, actually, yeah, I said I multiply by dt. So I'm actually just going to have, trying to remember. Yeah, that's right. That's right. Okay. Yeah. Yeah. So all I'm going to do now is basically have dt on the left-hand side, and the right-hand side is going to have dv over g minus b over m times v. So everybody understand what I did there? It's like I took a derivative symbol and broke it in half, which looks like something that I would have thought my calculus teacher would have told me was okay. But it is okay. And we'll see we'll see how it works out here. Okay, those little things I've mentioned before, they're basically like, you can call them what's called a one form, which is another type of vector. So if you have a really advanced calculus class, you can usually get that in the third semester of calculus, but you also get it in an actual class called advanced calculus. So anyways, let's multiply, or now that I've multiplied that dt through and got all the dv stuff on the left side, I mean on the right side, and all the time stuff on the left side, I'm going to go ahead and integrate it, and I'm going to integrate it from t equals 0 to t. That's really what's going on the left-hand side, but what's going on the right-hand side, even though I can still write it that way, what I got to realize is the thing I'm integrating is the velocity. Therefore, it's the velocity evaluated at t equals 0 and the velocity evaluated at t. So that's what the limits of integration mean on the right side. On the left side, it just means exactly what it is. So if I take the integral of dt, I just get t, and then I evaluate it at t, that's t becoming t, and I evaluate it at t equals 0, and I get 0. So the left-hand side is just t. So I now have t is equal to, in this case, what I want to do is I want to do a trigonometric I want to do a substitution, but not a trigonometric one. I want to let u equal g minus b over m times v. Then du will be equal to negative b over m dv. Okay, so if I had a negative b over m in front of the dv, then it would automatically be du, and I'd have the integral of du over u, which is really easy. So what I'm going to do instead is I'm going to multiply both sides of the equation by negative b over m. So this left-hand side, which was just t, is now negative b over m times t, times the integral of negative b over m dv over u, because remember the u was already there just by calling it g minus b over m times v. So I now have that. I've integrated the left side. I still got to integrate the right side, and this is from t equals 0 to t. So this now gives me negative b over m t is equal to, now this part right here that I now have written is just du. So the integral of du over u is just ln u. So I'm going to write down the natural log of u. So the natural log of u has to be evaluated at t and at t equals 0. So what I'm going to do is I'm going to say, well, u is g minus b over m times v. And I got to evaluate that at t equals 0 and t equals t. So now, next line, I get negative b over m times t is equal to the natural log of g minus b over m times v of t. I'll change this into a square bracket. So that's me evaluating the ln at the top limit of integration. Now I'm going to say minus the natural log. And remember what I said, v at t equals 0, which is defined to be v0, is just 0 for us. So when I evaluate g minus b over m times v at t equals 0, that v is 0. So I'm just going to get minus the ln of g. Now you know what the logarithms, how they behave. So the difference of logs is the log of the quotient. So that's what I'm going to use here. I say negative b over m times t, that's the left-hand side, is now equal to the natural log of g minus b over m v of t. I should probably, yeah, I'm going to do that a little better. So what I'm saying is negative b over m times v of t. And then all that will be divided by just plain g here. And now here's something to make the mathematicians squirm. What we can do is now I can take and raise e, the base of the natural logarithm system. I can take that e and raise it to the left-hand side of the equation's quantity. So basically I'm saying now negative b over m to the t times t is the exponent to e. And I can also take the e, the base of the natural log, and raise it to the ln g minus b over m times v of t over g power. So I can put that right there like that. Of course, there's cleaner, prettier ways of doing it that a mathematician would prefer, but this works just fine. So now what I'm going to do is remember the e to the ln of something just gives you the argument of the ln. So that's what's going to happen on the left-hand side. So now I'm going to have e to the negative b over mt is going to be equal to g minus b over m times v of t, all that divided by g, which with a little bit of work, you can actually see that it actually works out to be v of t is equal to mg over b times 1 minus e to the negative b over m times t. Okay, so just to roughly outline how I got that, because that was like 4 or 5 algebra steps in one there, depending on how you count the algebra steps or what steps you use. So basically what I did was I multiplied through by g to get rid of the denominator on the right. That gave me a g times the e that I have on the left. And then I ended up subtracting g e to the negative b over m times t. I subtracted that from both sides of the equation, and I added b over m times v of t to both sides of the equation. So the v of t ended up on the left-hand side, and the g minus g times e to the negative b over mt came up on the right side. And then all I had to do was get rid of the coefficient of m by multiplying, or excuse me, of v of t by multiplying by m over b. So that's how that came to be. You probably don't necessarily know what this function looks like, but I can show you really quickly. So it turns out, for starters, notice the e is raised to a negative power. So that means it's 1 over e to the positive power. So you can say 1 over e to the b over m times t. If you actually evaluate that at time negative, or excuse me, at time m over b, then you just get e to the -1 for that part, and that's 0.3786 or something like that. So that's something to keep in mind. So when I actually do graph this, the graph would look something like this. Okay, this is v as a function of time. This is time in seconds, say. That should be, of course, in meters per second, though I'm not really using any numbers, so it's not necessarily critical that I put that, but that would be the typical scenario. What we know is that the velocity at t equals 0 was 0, so we know that we're going to have a dot right here, right? Now, the other thing we know is that when I look at this function, if I let t go to infinity, then that becomes 1 minus 1 over e to the infinity. As e to the t approaches t equal infinity, with e of t in the bottom, that basically makes this whole term on the right inside the parentheses 0. So I'm end up getting basically an asymptote at velocity equals mg over b. So what I do here is I put up this little mark, say, and this will be negative, or excuse me, this will be mg over b. And I told you that it's sort of behaving as an asymptote, or it is behaving as an asymptote. So I'm going to draw it like an asymptote. And now what I can see is after one time constant, specifically t equals b, or excuse me, m over b. Notice when t equals m over b, you just get e to the -1 in that e term. So that's why I'm using that. Now, if I go up, what I will find is maybe somewhere in here is roughly where the next dot should be graphed. And if you follow that up and go over here, you're going to find it's about 0.63 times mg over b. That's what that value right there is. So now I can graph it. And it looks like that. In other words, there is a terminal velocity. And what that is when basically the v is equal to mg over b. And you can see why that is, because in the original diagram, I had a mass m, had a force acting on it of mg, and a drag force acting on it in the opposite way of bv. So if you set those two forces equal, you'd have the summation of the forces is equal to 0. That would give you mg minus bv is equal to 0, which gives you v equals mg over b. Does that make sense? Anybody have any questions on that one? All right, so that's a pretty good terminal velocity description. You can actually try numbers, use mass like 3 and b, just make that like 2 or something, and see how it works out and see how the graph looks and that kind of thing. That's kind of fun to play with. But that really closes off everything that I had to do in chapter 2. Chapter 3 is where we get into vectors. And as Vector said in Despicable Me, a vector is an object that has magnitude and direction. In fact, remember the villain's name was Vector, and he said it's a mathematical term. And he said it means it's something with a magnitude and velocity. And he says, and I named myself Vector because I do evil with direction and magnitude, right? So that's actually somewhat of a relevant quote. And it's accurate. So that really is it. And because of it being that way, it turns out that you can represent them as arrows, because an arrow has a length that we can pretend is like the magnitude. So, have a length in centimeters or millimeters or inches or miles or whatever. But that could also be converted to or scaled as meters per second. So maybe you make a scale where 1 meter per second is 1 millimeter. Therefore, if you have something that's 100 meters per second, then you just make it 100 millimeters long, and boom, you've got the exact right scale. It also has a direction. The direction is from the tail of the arrow to the head of the arrow. And therefore you can imagine what angle that arrow would cast on the x-axis. And you can imagine what shadow that vector would cause on the y-axis. And those are components and stuff like that. So a vector is a quantity / object with direction and magnitude. Magnitudes are generally positive. There's some weird ways you can do relativity that'll allow some magnitudes to be negative, and there's some special relativity and general relativity, and there's some quantum mechanics where you actually get magnitudes that are negative. But other than those really esoteric fields, you don't have to worry about a magnitude ever being negative. So that's one thing. We normally write them with a capital letter with an arrow over it. So a typical example for a vector would just be, let's say, this arrow right here, and we call that vector A. And in fact, if we took the time to measure this length from here to here, that quantity would be the magnitude, or at least would be the magnitude at some scale, right? Now, that vector exists whether you choose a coordinate system or not, but generally speaking, it's a lot of times it's easier to work with vectors when they are in a coordinate system. So what I'm going to do now is imagine that this is the positive x-axis and this is the positive y-axis, like that. And then we can define this little quantity right here to be theta. And notice I've measured it counterclockwise from the positive x-axis. So CCW from positive x-axis implies it's at theta. In other words, when you actually want to specify a vector to me, you could say a vector whose magnitude is 4 meters and points at 30 degrees, then I'll understand that that's exactly what you mean. You don't have to say north, south, east, or west, or relative to this or anything like that. If you just say the word at, then I know whatever coordinate system you drew, you're telling me the angle measured counterclockwise from the positive x-axis. If you went clockwise from the positive x-axis, that would be a negative of the angle. So, for instance, if this one happened to be such that theta is equal to 30.0 degrees, and such that the magnitude of A, which we really write like either this, or we write it with just the letter without the vector symbol. If that was, for instance, 2.00 meters, then we could say A equals 2.00 meters at 30.0 degrees, and that'd be a full description. But we could also use, if I measured downward from the positive x-axis, I could almost go the complete circle all the way around, right? But when I do that, I don't go the full 360, I go 360 minus 30. So another way I could specify this is 2.00 meters at negative 330.0 degrees. Other than that, those two special cases, you always have to say more than just an angle to give me the definition of a vector. Okay. Now, what I was talking about earlier was those components when I talked about shadows. So you could imagine a shadow down here and another shadow over here. And when you do that, this shadow is called A sub y, and this shadow down here is called A sub X, and it's a vector just like A sub Y is. Those are also called the components of A in the X direction and the Y direction. And that's what we need to start adding vectors. Time's now up, so I'll let you guys go with that. But we'll do some more vector stuff next week, and you guys are free to go. Do get your online test 1 done, and good luck.
I got a question before we go.
Yes, sir. Go for it.
So my audio cut out whenever you were doing the forces part. What does the B and B stand for? Those 2 variables?
What the B stand for? Yeah. So the mg is the object's mass, and
yes,
then
mass and gravity.
Yeah. That's just the formula for weight that you'll find out in the next chapter. And the B is it's related to your cross-sectional area and related to the properties of whatever fluid the thing is dropping through. So for instance, air would have a certain viscosity or a certain density, and it would relate those things. So that's what the B does. It takes into account the air or the medium as well as your cross-sectional area.
And V is velocity in that situation?
Exactly.
Okay, that makes more sense. Thank you.
No problem.
I had a question about formula sheets.
Okay, go for it. Just know if you can have them, or
like yeah, if we can use them on the exam, and where do we get like the approved one?
yeah. So I'm still working on making one for y'all, so that may not be done in time. So I definitely recommend you keep one that you can use for every test, in fact. But the online test, you're actually allowed to have open notes, open book, open internet. You're allowed to do Google searches, all that good stuff. You're just not supposed to get any information from someone who's already seen the test. So anything you can think of about to try to do that would be considered cheating. But other than that, everything else is golden. So far as the equation sheet goes, the only equations you're allowed are the ones that are in the book and labeled like with a next to the equation, either on the left side or the right side of the equation, or sometimes slightly up and to the left or up and to the right of it. There'll be like a parenthesis, and then it'll say 2-3, and that would mean equation 3 in chapter 2. So if it's got that kind of mark next to the equation, then that one's the one that's allowed to be on your equation sheet.
So for future tests, and like I know test 1 you say we use the internet, but for future tests, if I already made my own equation sheet, because I have like an equation sheet that I made that has the same equation written for different variables, like just did the math already, so I can just plug it in.
Yeah, that's not a problem. Well, it's sort of a problem in that if you took the time to write the equation and then solve it all the different ways, then you're not going to find that numbered in the textbook. So in other words, we only want you using the equations that are numbered in the textbook, except for the few cases as the semester goes along where I'll make up one myself and say, this one isn't numbered, but you're allowed to have it on your equation sheet. So I'd say you probably can't use that, and you might want to get, I get what you're doing and why you did it, but you just might want to do a little bit more practice about solving those equations. If that's going to give you a problem anyways. I doubt it will. I'm sure you're still going to be fine, but.
Okay, cool. I appreciate it.
No problem. And
All right, I have
Eddie, you're the last person, so you can ask away. Do you want me to stop recording because you're going to ask me questions that you don't want anybody knowing about?
It's fine. You stop recording.
Okay. So you said I can keep it recording?
No, you can stop it. That's fine.
Okay, gotcha.
All right. So on those kinematic equations, which ones are we supposed to know exactly, or which ones do we need to pull from?
Just the ones that are numbered. So like, let me do a share screen with you real quick. And this time I'm going to use this screen, and I'm going to scare you with chapter 19 again, but I'm trying not to. So let me jump to chapter 2.
I thought I was in Genesis for a second.
Yeah. Yeah, so I think it would be right here. So you see all these equations, they don't have anything by it, so they're supposed to not be on. But this one right here has a 2-7. That means one of the equations you're allowed to write on your equation sheet. There's another one.
What's that?
There's another one.
2-2. You see how it's hyperlinked? Is that something different?
Yes, that's something entirely different. So it's only the equations that are, well, if you actually go to this one and you click on it like you did there, notice it is actually numbered.
Yeah.
That's the whole reason they have that number system, so they can hyperlink it back. So yes, in general, if it's got like that, that means that that's probably one that you're going to be able to do too. But yeah, the main thing is as you go, you look at each section, and every time you see one of these, you can copy it down.
Okay.
Okay.
And I mean, how do you know which ones to use?
That's the trick of what you're learning in the first and second chapters, more so in the second chapter. But you learn those equations and you learn what the individual symbols mean, like A is an acceleration, V is a velocity, V0 is a velocity at t equals 0. Sometimes V with a subscript I will be used, and that means V initial, or sometimes V with a subscript F will be used, and that means V final. And
so
go ahead.
VO is not the initial velocity.
That's another way they can do too. They'll write an O or a 0.
Oh yeah. So V sub 0 is initial velocity, or really, it's really the velocity at time 0.
Exactly.
Okay. Which is initial, obviously.
Yeah,
Okay,
and you can not only that, as you're reading the problem, it'll have numbers, and the numbers usually have units with it, and they have a unit. So if you actually know the units of the quantities, that helps you too. So if you forget, which one's velocity or which one's acceleration, obviously the units will tell you, even though obviously there's some V with velocity and A with acceleration correlation going on.
Right. Yeah, so here's another issue. So I'm currently taking Calc 1.
Mm-hmm.
So I am learning about limits and derivatives right now. So integration is not something I'm at yet. So when you're doing that, I have no clue what's going on.
Gotcha. Okay, so we've got a major problem here. You're technically not eligible to take the class. I don't know who let you in, but that's a bad thing. I will work with you as hard as I can to help you stay in if you want to, because we've gotten so far in the semester. I will, move heaven and earth to help you. But you're also completely eligible to be told that you can go down and say, hey, I'm sorry, I need to withdraw from this class and I would like my tuition back. No one was supposed to let me sign up for this. I think it's probably the policy is that it's the student's responsibility, but you probably got a good argument for getting them to get your tuition back if you want, for this class at least.
Yeah, so you do a lot of integrals in this class?
Okay, you're not in this class. You're one of my students from 202, right?
No, I'm in this class.
Okay, are you? Gotcha. Okay, yeah. So
yeah, we're doing integrals already, and I don't even I haven't gotten there. I'm still on derivatives.
Yeah, it's like I said, I can help you. You'll learn the formulas of derivatives. You probably should be learning them already, like x to the n, the derivative is n times x to the n minus 1.
Power rule, exactly.
Yeah.
So I mean, I'm pretty sharp, I think, with derivatives. I got, you know what I mean? I can I know the quotient rule, product rule, I can do limits. But integration, I'm just not there. Or anti-derivatives, I'm not there. I don't know anything about those yet.
Gotcha.
So,
well,
I mean, is that
what's the opposite of subtracting 1 from n? See if you know that.
The opposite of subtracting 1 from n?
Uh-huh.
Are you talking about exponents or just n minus? What's the
yeah,
opposite
like the
of
exponent? Like I was telling you, the formula for the derivative of x to the n is n times x to the n minus 1.
Right. Correct.
Okay. So what would be the opposite of subtracting 1 from that exponent?
Adding 1.
Yep. And in fact, the formula for the integral of x to the n is partly x to the n plus 1.
Okay.
So that's the complication. Now, the other part is n the initial or the final exponent? because the derivative of x to the n is n times x to the n minus 1. So
But
is
wouldn't
that,
it be the initial?
yeah, it's the initial, right? Well, since that one's the initial one, and it's being multiplied by, the opposite of the initial is the final, and the opposite of multiplication is division. So the integral of x to the n is x to the n plus 1 over n plus 1. Boom.
Oh,
So that's literally the complication. So like I can help you make it through it. I do not recommend it, but you know, we're 3 weeks in and I had no idea. So if you're wanting to shoot for help, I will do what I can to help you get out of the class, or I'll do what I can to help you stay in the class. Doesn't matter.
that's kind of a big deal. I thought it was a this whole time too.
Well, we have another class that we offer that's algebra based, and that's 201. So you could have taken that. But
That
most
doesn't sound.
degrees that you're thinking of probably do need the calculus based one.
I'm doing the engineering degree,
Yeah.
so I'm.
There is one book that was written by a guy by the last name of Hecht, Hecht. He taught this course as if it was meant to be taught simultaneously with Calc 1. But that's literally the only time I even knew of anyone writing a book for it. And it was because of it, I really did not like the book because we didn't get to what we needed to get to in time. That's part of the thing where I'm trying to tell you that I can still help you, because it's very, very normal that you're always going to learn your math, or a lot of your math, in your science and engineering classes before you ever get to them in your math classes.
Right. So when you first brought up the integral, I figured that was the case. Like, oh, we're going to learn some integral, but you know, you teach it because we're already supposed to know it. So you're not like teaching us integrals. You're just using it.
Exactly. I'm just doing integrals. Yeah,
right. Exactly.
You're free to, I mean, that would be a good thing to write down, like in the margin of your notes. And then at the end of class, you know, say, how did you know the integral of sine was this? And I'll just give you the rule. And really, a large part of integration is knowing just the formulae.
Right. You know, for example, derivatives, like the first derivative of sine is cosine, first derivative of cosine is negative sine. So like, but unless you know that, you don't know that.
Yeah.
Right.
Just remember, you said the word antiderivative. That's why I was using the arguments of what's the opposite of n minus 1, what's the opposite of initial, what's the opposite of multiplication, because that turns out to be exactly the opposite of derivatives. Integrals, antiderivatives are the opposite of derivatives. So for instance, when you say the derivative of sine is equal to cosine, guess what? The integral of cosine is equal to sine.
Oh, wow. Interesting.
And you said the derivative of cosine is negative sine. Well, guess what? The integral of negative sine is cosine.
Oh, that just blew my mind.
So yeah, and you will have ample practice with the math that we're doing, just because I do it in the class and you do it in the homework, and you know, I can help you when you run into a logjam on that. So like that, I will do anything I can to help you succeed if you want to stick in the class. And I also realize, and this might be something you don't know, but students, if they get any kind of aid or anything like that, if they drop below full time, then one, sometimes there's ramifications for their aid. Another thing is sometimes they're no longer allowed to be on their parents' insurance, medical insurance. So that's why I'm really trying to say, hey, if you need to stay in the class, then I will help you as much as I can.
Understood. Oh, well, I guess I got some soul searching to do, honestly.
Yeah, you do. If this book actually has appendices in it that has the table of integrals and table of derivatives, which you're somewhat into derivatives already, so you know a lot of them. And that's pretty much all we need is derivatives of e to the x, polynomials, and trig functions. And that's pretty much all we need to know with regards to integrals, at least in 241. When you get 242, stuff gets really crazy.
Okay, well, I guess that's my next question. What is the prerequisite for 242? Is it Calc 2?
No, it's Calc 1.
It is Calc for 242.
Yeah, and I think they might have it listed as 242 being a co-requisite or something, or Calc 2 being a co-requisite. It might have something like that in it, but yeah, it's not Calc 2.
Okay. Right on, because I was like, oh, well, I'll just be in the same situation next semester because I got to take 242 also.
Yeah, and I teach all that math specifically because I know we're getting ahead of the calculus class, and sometimes we're getting past where Calc 3 goes. So I do a lot to try to help people with that. The students are usually successful, so you know I can do that. But yeah, you are definitely in a tight spot, so definitely think about it. You know, let me know what you need. If you do decide you want to drop, you're going to have to petition for that, and you'll have to talk to my dean, and I'll back you up, you know, 100%. Or if you want to stay, I'll back you up 100% too.
Okay, I definitely appreciate that. What's your phone number if I need to get a hold of you?
Okay, I'm making sure I don't have it. Yeah, I'm not recording anymore. So yeah, my phone number is 252. Oh, wait a second. Damn, I've been recording this all the time.